In this video, we are going to look at the mechanism of ATP synthesis through oxidative phosphorylation and how the ATP synthase mobilizes this electrochemical proton gradient to produce the ATP. We also look at the structure of the ATP synthase that enables it to synthesize the ATP through oxidative phosphorylation and how the synthesis is basically done by the various subunits of the ATP synthase. We discussed how the electrochemical proton gradient is created in the inner mitochondrial membrane in the previous video. I will encourage you to go back to the channel and search for that video and watch it. I think about 2 videos before this, and watch how this gradient or this electrochemical proton gradient is created in the inner mitochondrial membrane, which the synthase used to synthesize ATP. We are going to move a bit slower today because the systematic addition or the process is quite of complex and it's going to be technical, so we are going to move a bit slower today. So let's first look at this structure here. As seen here, this membrane, this bilayer membrane, is the inner mitochondria as we looked at in the previous video. If you look at this, if this is the inner mitochondria membrane, outside here is the intermembrane space. This space is between the outer membrane of the mitochondria and the inner mitochondrial membrane. This space is where we have the several concentration of the protons or the hydrogen ions after the electron transport chain system. In here is the matrix of the mitochondria where the synthase opens to. So the matrix of the mitochondria is where the ATP synthase is basically okay. That is the oxidative phosphorylation. The inside membrane is where the transport of electron okay, and the intermembrane space, which is the space between the inner mitochondrial membrane and the outer mitochondrial membrane, is where the protons are pumped. This gradient is what the ATP synthase uses to produce or to synthesize ATP molecules through oxidative phosphorylation. So let's look at first the structure of ATP synthase and discuss a few of the mechanism of the ATP synthesis. And in the next video, we're going to look at into details how basically the phases and the chemistry behind the synthesis of the ATP through oxidative phosphorylation. So let's look at the ATP synthase structure, which is the main enzyme which is involved in the oxidative phosphorylation. So as seen here, this is basically the structure of the ATP synthase as seen here. So as we discussed, where the hydrogen ions are is the intermembrane space. So this side here is the intermembrane space as we looked at here. The hydrogen ions accumulate in the intermembrane space, and where the ATP synthase opens up to is the mitochondrial matrix. So this side is the mitochondrial matrix, and up here is the intermembrane space. The ATP synthase basically has 8 distinct subunits. But each subunit might have one or more subunit. So as seen here, this is the structure of the ATP synthase, which is embedded in the inner mitochondrial membrane and opens into the mitochondrial matrix. So seen here, part of it is embedded in the mitochondrial membrane, and the part opens down into the mitochondrial matrix, as also shown here. This membrane is the inner membrane. This part of the synthase is embedded in the mitochondrial membrane, and this part is opened into the mitochondrial matrix. It has 8 distinct subunits, as we said earlier. It has a C subunit. It has an A subunit, which is between the B subunit and the C subunit. More clear here. The A subunit is between the C subunit and the B subunit. It also has an alpha subunit, a beta subunit. It has a gamma subunit. It is a delta subunit and an epsilon subunit. So it has a subunit, which is between the B and the C. It has a delta subunit. It has an alpha subunit. It has beta subunit, and epsilon subunit and a gamma subunit. Basically, the ATP synthase has two main parts. We have the F0 part and the F1 part. The F0 part is the part of the synthase which is embedded in the inner mitochondrial membrane. So this part is the F0 part, which is embedded in the inner mitochondrial membrane. The F1 part is the part which opens up into the mitochondrial matrix. So this whole part of the synthase is the F1 part. So the ATP synthase is also called sometimes F1, F0, ATPase because it has two main parts, the F1 part and the F0 part. The beta subunit or the B subunit has two parts. It has 1, 2. The B subunit has two subunits as shown here. The C subunit has 10 different subunits. The C subunit alone has 10 different subunits. The beta subunit has 3 subunits as shown here. The beta has 3 subunits. The beta forms part of the F0 subunit. The beta forms part of the F1 subunit. And we have 3 beta subunits which form part of the F1 subunit. We have 3 alpha subunits which also forms part of the F1 subunit. Now the gamma here serves as a shaft which connects the F0 to the F1. So it basically connects the C subunit to the beta subunit. This gamma here serves as a shaft which connects the F0 to the F1 through binding to beta. I think it has connection with the delta subunit here. The beta subunit basically is the catalytic subunit. That is the subunit which is meant for the synthesis of the ATP. So the catalytic subunit of the ATP synthase is the beta subunit. The subunit mainly for the synthesis of the ATP. So this is just a summary of the structure of the ATPase. Now let's look at a brief mechanism of how the ATP synthesis occurs through oxidative phosphorylation. Now, as we established in the previous video, after there is a flow of electrons from the various complexes of the electron transportation system, from the electron equivalent, that is the NADH and FADH2, the accumulated protons outside or the in between the inner mitochondrial membrane and the outer mitochondrial membrane, which is the intermembrane space, flows systematically from the space to the matrix, which enables the ATP to be synthesized. Basically, after the flow of electrons from the various electron equivalents to the final electron carrier or acceptor, which is oxygen, we get to accumulate several molecules of protons in the intermembrane space, and these protons flow back to the mitochondrial matrix, which enables rotation of the C subunits, changing the conformation of the beta subunits for ATP to be synthesized. Let's get into it. When we have several molecules or several ions of the hydrogen in the intermembrane space, sequentially, the C subunit has two canals. It has an entry canal for the hydrogen ion. The end of the entry canal is a deprotonated aspartate amino acid. A deprotonated aspartate amino acid. Now it has an exit canal where the hydrogen, which also is also exited from it. So the end of this canal is a deprotonated aspartate or an aspartic acid. So when it gets here, it flows sequentially. That is, there's going to be a rotation of this subunit to it till it gets here before it exits. Let's see something here. If you have a hydrogen atom entering the entry canal of the C subunit, basically the C subunit sometimes is called the rotor, as in it rotates. So as shown in the arrow, there is a possible rotation as the hydrogen atom enters here. What happens is when the hydrogen ion enters the canal, it causes protonation of an aspartate amino acid here. So this, as the case on this one, is an aspartate amino acid. When hydrogen ion protonate the aspartate amino acid, it creates a potential, and that potential enables the C subunit to rotate to an angle of 120 degrees. One hydrogen ion causes protonation of the aspartate, and the aspartate creates a potential that is more of a membrane potential around the C subunit that causes a rotation through an angle of 120 degrees. So per the protonation of 3 aspartate amino acid, there's going to be complete rotation of 360 angles. And that 360, by the time we get that 360 rotation, the first aspartate will get here and it will leave that hydrogen. So it gets here and gets protonated. When it gets here, it will deprotonate that hydrogen back here. So 3 hydrogens are required for complete rotation of the C subunit before one hydrogen ion can exit the C subunit. The C subunit is the main part of the F node, which is also the rotor. So when it gets protonated, it shifts or it rotates through an angle of 120 degrees. So when there is a protonation of 3 aspartate ions or amino acid, what is going to happen is going to be a complete rotation of 360 degrees, and that causes the exit of one hydrogen ion. So that's how basically the rotation of the C subunit occurs. Now let's see how the ATP synthesis occurs here. Now the gamma subunit is bonded to the C subunit. It serves as a shaft between the C subunit and the beta subunit through an interlinkage with the delta subunit. So when there's complete rotation of the C subunit, the gamma subunit also equally rotates. And when it rotates, the beta and the alpha subunit also rotate in the same manner. Now, as I said earlier, the beta subunit is the catalytic subunit, which is meant for the ATP synthesis. At every point in time, each of these beta subunits will exist in one conformation. The beta subunits can exist in 3 conformations. It can exist in a very tight state, which is bonded to an ATP molecule. It can exist in a loose state, which is bonded to an ADP and a phosphate, or a very loose or an empty state conformation, which is bonded to nothing. I take it again. The beta subunits exist in 3 conformations. The beta subunit exists in 3 conformations. It can exist in a very tight state. The tight state is bonded to an ATP molecule. It can exist also in a loose state, which is bonded to an ADP and a phosphate. Or it can exist in an empty or a loose state, which is bonded to none. So as soon as a conformation or a state of a subunit assumes a tight state, it means it will get bond to an ATP molecule. When it exists in a loose state, or let's say there's a loose state, it will have an ADP and a phosphate group bonded to it. Now when it changes to a very loose or an empty conformation, it will release out the ATP molecule. So the conformation of the rotation here, the main aim of the rotation here is to cause the various subunits to exist in an empty or a very loose state so that it can release out the ATP which is bonded to it. When there's a protonation of the aspartate, as we caused here, there is a sequential rotation, and when there is complete rotation of the C subunit, which is caused by protonation of 3 aspartate amino acids, what happens is there is a complete rotation of this center or the subunit, and we are going to, at that time, we are going to have the 3 conformation, one of them going to be existing in a very loose or an empty subunit or empty conformation, and that empty conformation causes the release of one ATP molecule. When there is protonation of 1 or 3 aspartate, there is a complete rotation of the C subunit, and that complete rotation causes the conformation or the 3 subunits to totally rotate and let one of the subunits assume a loose or an empty state, which causes the release of an ATP molecule. At a point in time, let's say an ADP might bond it to one of the subunits together with a phosphate group. So when there's complete rotation, it will change back to a very tight state. It comes back to an empty state so that it can release back the bound ATP molecule. So basically, we need 3 hydrogen ions for complete rotation of the beta or the 3 beta subunits, but we need 4 hydrogen ions for the synthesis of 1 ATP molecule. Take note. Now the 3 hydrogen ions are needed for complete rotation so that we can cause the conformations or the subunits of the beta to exist in an empty state to release the ATP molecule. But the additional 1 hydrogen ion is required for the transport of the ADP and the phosphate from the cytoplasm or from the intermembrane space to the matrix. So we need an equivalent of 4 hydrogen ions for the synthesis of 1 ATP molecule. In the next, we are going to look at into details how basically what really happens in terms of mechanism and see what causes, how the flow of hydrogens causes the beta subunits to equally conform to change to an empty state so that it can release the ATP bound. This is a very short tutorial on the structure of the ATP and the mechanism of ATPase and the mechanism of ATP synthesis through oxidative phosphorylation. Thanks for watching. Don't forget to subscribe so that you can receive a notification update from this channel. Stay tuned.